So very good morning to all the participants and very good morning to Hardev Saab, today's faculty, and he'll be he'll be talking about the dam instrumentation and monitoring. Shall we wait for 5 minutes more because more participants are joining, and then we shall start it. Up to now we have done. Up to now, we did nine sessions. So we have completed 9 sessions of this webinar series. We have started this webinar series on 5th of November, and every Tuesday we do it for 2 hours approximately, or 2.5 hours completely. And that means we have started it from the Dam Safety Act implementation. And then we covered this Dharma tools for data entry, and then session was also done on this dam inspection. All these sessions were covered by NDSA officers. And then we have done this hydrological safety review. We are doing this webinar series for dam safety aspects, and we have selected all topics covering the dam safety, and then reservoir rule curve that was also covered by one eminent faculty, and then emergency action plan, dam break analysis. We have covered rapid risk assessment of the dams, existing dams. Also, lastly on 31st December, we have covered these geophysical methods of assessment of dam health. So we covered 9 topics, and today is we will be talking about this dam instrumentation. That is the 10th session of this webinar series. Total, we have taken it 15 sessions. So this webinar series will be up to 11th February. And then almost all topics will be covered of these dam safety aspects. From participant side, also they are very interactive. All the sessions were very interactive in past also. This dam instrumentation, we have conducted one training program of 1 week complete at NWA Pune 3-4 months back. And this topic, as we say that all topics of this dam safety aspects needs at least 1 week coverage of the complete sessions. But this webinar series, we have limited our time for 2.5 hours only, 2 hours only, and in that means it is not possible to give all the perspectives of the topics in such a short time, because all these topics require completely 1 week. I hope that all these topics have been detailed by our speakers in past, and they have they have done. Participants were more active. They were they raised many questions, many queries, and all queries were discussed here. And we are definitely, I hope that participants are getting benefited from this webinar series. So anybody can speak. Anybody can talk about this webinar series, and we have a 5 minutes more time to start the session. It's a 10:35. Almost 100 participants have joined it, and in 2-3 minutes. Otherwise, better if you are not you have no any talking point, then I will start the session. Very good morning. Now I am starting the session of this webinar series, today's session. Very good morning to all the participants. Very good morning to all the our faculty, today's faculty speaker, Sri Hardev Saabji. He is a scientist in CSMRS. Before the start of the session, I'll briefly talk about his experience. Sri Hardev Sri Hardev ji graduated in civil engineering, and after that he did a post graduation in water resources development from University of Roorkee. Now that is IIT Roorkee. After that he joined Central Soil and Material Research Station, one of the premier premier research station in material means research. He was associated with investigation of more than 120 water resources projects. He is associated in more than investigations of more than 120 water resources projects in India and its neighboring countries like Bhutan, Nepal, and Myanmar. He also worked in Tala hydroelectric project, THPA Bhutan, on deputation, and looked after the quality control and instrumentation works of all the civil and hydromechanical works of Tala HEP, that was 1020 megawatt. Worked in Department of Scientific and Industrial Research also, and then means he is having right now he's having more than 34 years of experience in technical and managerial capacities in rock mechanics and rock engineering, including investigations of river valley projects, quality control, instrumentation, and tunneling for hydropower projects. And he also contributed more than 150 research papers in various international, national journals, conference, seminars, and he is honored with prestigious outstanding contribution to rock mechanics award for the year 2018 for his contribution to rock engineering by Indian Society for Rock Mechanics and Tunnel Technology. Received best paper awards also in journals and conferences. He is a member of expert committees in tackling geotechnical problems in hydropower, landslide, and tunneling project, and delivered numerous lectures in different institutions on all these topics. And he also drafted many Indian standards on the subject, new subjects also, and suggested many revisions in the existing subjects of this water resources WRD component of the BIS. Means I welcome sir. I welcome Hardev Sahab, and I request him to means I invite him to start his talking. Yes, just one thing I forgot, that means as we do in all the sessions, that means participants are means requested to write questions in the means chat box, and at the end of the session, all those questions will be taken by our speaker and one by one. That is not hard and fast. You can intervene also in between if it is required, but that will be a systematic things, that if all the queries comes in the chat box, and one by one will be answered after the session, after end of the session. So Hardev Sahab, I request you please start the session.
Okay, thanks. Am I audible? Dasab, am I audible?
Yes, sir. You are audible.
Okay, okay. First of all, thanks, Dasab, for such a nice introduction. And before I start, so shall I? Sorry. Shall I share the slide? Okay.
Yes, please.
Yes. Let me share the screen. First. इसको PPT में. Yeah. Is it visible?
Yes, sir. It is visible, sir.
Okay. So thanks a lot, Dasa, for this nice introduction. So today I will be talking on the dam instrumentation. So the need and importance, and some case studies will also be shared in this session. So dam instruments, coming on to the dam instrumentation or the other hydraulic structures. So instrumentation is part and parcel of any dam and other hydraulic structures, be it a dam or some underground structures. So without instrumentation, I think we cannot assess the safety of the dam during construction as well as in the aging dams. So instrumentation is, I think, quite important and significant in assessment of dam safety. It's a very vital topic, and thanks NWA for choosing this subject. So during the 5 days training course on instrumentation in dams at NWA Pune, organized 3-4 months back, the same lecture was delivered by me. Both the lectures were delivered, and it was well received during that period also. And I'll try to cover the need of the instrumentation, the kind of what kind of instruments and should be installed, what parameters, and then with some case studies of dams. So I'll try to do justice with the subject. So now, before I start the instrumentation, just a background of CSMRS, just 2 minutes I'll take. So established in 1954 as silt analysis, maybe it was a directorate of Central Water and Central Water Commission. So Central Soil and Material Research Station was directorate of Central Water Commission way back in 1954, and later on in 1981, one committee headed by Dr. M.S. Swaminathan was formed, because what was happening as a directorate of Central Water Commission, the people used to come over to this station, and then after 2-3 years they were being transferred to other places as a routine thing. So that committee felt that we are not able to develop the expertise in geotechnical investigations and material testing. Then they recommended that CSMRS should be a separate entity under direct control of the ministry. Then in 1981, it became Central Soil and Materials Research Station as an attached office of Ministry of Water Resources at that point of time, now Department of Water Resources, Development and Ganga Rejuvenation. So our core strength is basically in soil, rock, and material investigations, concrete and other materials. So apart from that, we are expertised in instrumentation and monitoring, geophysics, and some other geosynthetics and other allied subject areas. Nowadays, because of the Dam Safety Act in place, so we are involved in dam safety assessment of the aging dams, health monitoring of the dams, so which includes non-destructive testing on the concrete structures, geophysical investigations for the earthen dams as well as for the concrete dams. And we have completed many projects during the past 1 year or 2 years, particularly 2 years. So many aging dams have been diagnosed by CSMRS, and many issues and the kind of distress wherever is there. So those have been reported and are being taken for rehabilitation and repairs. So this is this complete short background on brief background on CSMRS and its activities. So I'll start on the today's subject, instrumentation. So there's one quote. I usually start with this quote, Lord Kelvin, a British scientist. When you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot express it in numbers, your knowledge is of a meager or unsatisfactory kind. So taking this quote as, if we say that, suppose we are doing some instrumentation for a dam or any other structure, we say that the deformations were negligible, the deformations were very small, there were large deformations. We usually use these terms on the basis of the visual inspection or the visual monitoring. But but that doesn't serve our purpose. So maybe the deformations which one can say that it is too large, but when going in numbers, that might be within the safe limits. So expressing anything in numbers. So rather than saying that the deformations were very small or very negligible kind of thing, if we say it is 10 mm or 15 mm or so, or for example, the deflection, dam deflection. So if someone says on the visual inspection that it is safe or something like that, but no major deflection is there. So if we have some number, we have some data from the normal plumb line or inverted plumb line, then we can say the deflections are 5 mm at the maximum flood water level. Then those things are quite meaningful. So this way we can talk in terms of quantitative language rather than the qualitative. So instrumentation and monitoring combined with, so we can say it's a vigilant visual observation, can play early warning. So the monitoring, the first thing is the visual monitoring, by which we can see or through our naked eyes that some distress or some sometimes we hear through these ears also. If some sound is there, whenever suppose we are walking in an underground environment, you hear some kind of sound from your adjacent rock. So those ears can also play a good monitoring tool. So in this sense, our eyes and ears can play an important role in monitoring or diagnosing or assessing any issue or problem with our construction of our structures. Thus, we can say the instrumentation is the collective term for measuring instruments which indicate something. So let me clarify it. These instruments indicate something. They indicate something in terms of numbers. And those numbers have to be further analyzed and interpreted with regard to our structure, with regard to our design values. Then those things can be analyzed and rather reported. So instrumentation is basically, though instruments indicate something, these parameters are measured, and these instruments record those parameters in physical quantities. So coming on to the number of large dams in India, India is ranking third in the world in terms of the large dams. So this is the data from 2023. So almost 5,700 large dams do exist in India. But the status of instrumentation is, I think I'll say, quite dismal. Though the field instrumentation was initially started in way back in 1930, but still, if I talk in terms of the dam population in India, so almost about 5% of these dams are instrumented. And coming on to the meaningful instrumentation also, the out of those 5% also, our experience says is very dismal. Very dismal. When I say very dismal, so it is a term that a bit relates to the installation, monitoring. If we do monitoring, then we don't do any analysis or interpretation. And even we do some interpretation also, then the data is not being properly utilized for the design verification or for the rehabilitation or remedial measures. About 50 years ago, if I say, the instruments were not usually specified, but some of the instruments, those mechanical instruments, were already in place, which were used to assess the performance of these dams. So during those periods, instruments were installed only when the problems were encountered, rather than using them as a precautionary or the warning measures or the or the instruments which can tell you, which can act as early warning signals. Today the situation has changed, but the instrumentation is generally specified in each project proposal, and our Dam Safety Act also stipulates that instrumentation should be part and parcel of our dams. So still needs to do a lot of meaningful instrumentation. So that is our experience shows that during we are involved in instrumentation during the construction of dams also, during operation and maintenance also, and during the planning stage also. So we are involved. So our experience is, so still needs to do a lot for meaningful instrumentation. So why instrumentation? Let's understand it with this visual. So, because suppose you go to any doctor that for prescription or for some any disease, but doctor takes a pen and a paper, and then he usually starts writing while asking you. He asks many questions to you regarding your uh, symptoms or something like that. What do you feel or something like that? He writes, okay. And maybe you may not be in a position to tell all the information regarding to your disease, but he writes, and on the basis of the, suppose he recommends the medicine on the basis of it, then it may not be worth, or it may not be, it may not serve the purpose. So then what he do, he just takes out one thermometer or one stethoscope and measures something, and if he feels something, then he recommends some sort of further investigations, and on the basis of that, those investigations, he recommends the treatment for this. But suppose he acts on the information which you provide to him, that may be disastrous. And similar thing is with the dam instrumentation also. Visual inspection is all right, but installing some instruments and getting some physical parameters, quantities of those parameters, that is more important. So basic aim of instrumentation is, I'll say, it's the minimizing risk, and dams are no exceptions. So instrumentations help in minimizing the risks. The risks can be avoided or minimized by inspection, continuous monitoring, and then analysis of that monitored data. And then on the basis of the interpretation and analysis, you recommend certain things, and those remedial measures or timely remedial measures or corrective measures are taken. And later on also, the instrumentation can provide you the information about the efficacy of those remedial measures. So you need critical scientific measurements in instrumentation. Engineering behavior of structure under different loading conditions. Dams are built in stages, and in each and every stage, you go on monitoring the different parameters or detections of symptoms of distress with right instruments. You have to locate, you have to choose the right instruments for right measurements, right locations, at right moment, and at right interpretation is also required. So risk management includes identify those risks, and then assessment of those risks, and then control those risks, and then finally you review those control measures. So purpose of the instrumentation is detecting distress at early and preventable stage. So instrumentation doesn't protect our structures as a whole, if I say, but protect in an indirect way. It gives you certain, provides you the information at an earlier, when the those distress can be prevented through recording quantitative data analysis, again, similar things. Those, and the secondary purpose of the instrumentation is the designers certain take the input data from the geotechnical investigations and the material properties, but sometimes they assume certain parameters take those parameters derived from the empirical correlations or the earlier experiences. So it is not necessary that all the information or the input data being used is has been actually performed from the actually performed tests in the field or from the lab, but certain parameters are still being assumed by the designer based upon the experience. So instrumentation provides you the response of the structure. So the predicted response as well as the observed response, you get the information about the performance of the structure under different loading conditions, and then verification of design accuracy. Through this, we can verify the design accuracy, adequacy. Then based upon this instrumented data, so we can do some refine the design in similar structures, or we can uh, go for some revision in designs also. So this provides. So this is one example of Grada Dam, which was being constructed in 2003, 8 or 9, something like that. And what happened actually, it's a 30-meter high earthen dam. And while first filling in 2010 after completion, the portion of the closer section breached on 15th August 2010. When the water level was at the highest almost, it was during the first filling itself, it breached. So this was the condition after the failure of this Grada Dam. And later on, of course, the examination or the causes of the failure were analyzed or deliberated, and these are some of the things which were not taken care or which were not completely followed. So instead of the homogeneous section was designed against the zoned dam designed or the proposed. No detailed investigations of the foundation material was undertaken before construction, and dam closure, which usually should be completed within the one season, so it was completed in 3 years. And much deeper constructed embankment slope, steeper embankment slope was there. And then much thicker lift thickness, that is also specified. You have to follow the guidelines or the design as proposed in the design. And no arrangement for controlling the reservoir filling rate. That is a major mistake which was found there. So depth of water from almost 14 meter was completed in 20 days itself, and maximum rise of the order of 11 feet in a day, 3.4 meter. A day before, the rise in water level was almost 1.8 meter when it failed. And at the time of failure also, the reservoir is in rising trend. And then while inspecting the foundation conditions, it was observed that the jointed, fractured rock mass was observed. No sealing of joints was undertaken. No proper filter arrangement was there. And of course, that is a most important thing. No instrumentation was designed. Had there been some instrumentation has been taken up in earthen dam, if we install some piezometers on the taking some certain sections, then it will provide you the information about the piezometric heads at different sections, different on the downstream slope. From there, you get the idea that how your phreatic surface is being generated. So before you can get some information before the failure actually takes place, and you can avoid the failure rather. So after that, the rehabilitation started. Of course, rehabilitation is time consuming, costly, and requires some additional resources. And then so rehabilitation works were taken, and then now during the rehabilitation stage, the foundation investigations were done in a detailed manner, and the curtain grouting was done, and of course the mapping was of the subsurface ground conditions was done, geosynthetic layer was done. So we did all the precautions on take the revised the design also. So it was rehabilitated back in 22, and now it's in operational mode. So coming on to Bhakra Dam, it's a 225-meter high concrete gravity dam built across river Satluj, completed in 1963 with a storage capacity of 9.3 BCM. Why I am taking this Bhakra Dam is because this Bhakra Dam was designed by USBR, Colorado, USA, by trial load analysis. And after the completion of the project also, the reanalysis was again done with respect to the stability and structural adequacy. And the computed maximum deflection of the dam, as per the studies in 1964, after completion, after reanalysis, as specified by USBR, was 1.53 inches, 38.86 mm for seismic condition, and 1.03 inches, 26 millimeter for non-seismic condition. Deflection in block 20, which is the deepest block, it is normal plumb line is also situated there. It shows increasing trend, and during the years of 1995, 98, 2008, 10, 2011, 13, maximum deflection has been surpassed. 26 millimeter deflection has been surpassed, and of the maximum deflection as on duty today measured so far is 1.11 inches. 28 millimeter has been observed at reservoir level of 1670 feet or 509 meter. So with this, although the dam is showing no visible signs of distress, seepage, or problems, but this maximum deflection, this is an issue, and the dam owners are taking care of this maximum dam deflection, and they are probably the maximum storage level has been fixed as 1670. Beyond that, they will not allow storage of dam. So in view of the safety of the dam, this is the latest example of distress in our dam. This is one of the barrages, Medigata barrage in Kaleshwar Dam. So one of the block sunk by more than around 1.2 meter. So although the investigations for causes of distress and then remedial measures are on, and probably we will get a solution to it, and we can rehabilitate this structure for use. So from the dam failures, we learned some lessons. The post-failure measures are much costlier than ensuring dam safety at early stage. Suppose we do instrumentation during construction or during operational stage, then that might be more that will be good for the structure. Failures are not abrupt, rather catastrophic in nature. So it doesn't fail abruptly. So it gives you some ample time before the stresses, deformations the deformations exceed the minimum or the permissible values. So ultimately, during failure, we witness loss of life, property damage, or environmental degradation, high hazard dams near populated areas. So many things are there. Though dams failure of probability is quite low, but their consequences are very high, and sometimes these are devastating in nature. So coming back onto the objective of the instrumentation, the basic aim or the objective of the instrumentation is to develop safe, cost-effective, and reliable structures. So instrumentation can play a vital role in this. So instrumentation can be used for site characterization. So many parameters are being defined on the basis of the field and lab instruments. And as I have already told that designers design the structures on the basis of certain input parameters and take into account or define the maximum or the permissible values of different parameters, and to validate those assumptions or those parameters, with the actual response of the structure, we need the instrumentation. So instrumentation provides you the observed values of these parameters under different loading conditions, and by that way the designers can gain confidence with the assumed behavior of the structure, or they can go for certain changes or modifications in the design. So instrumentation can also be used as construction control. Those can be used for adequacy of contractors, methods, procedures, or some midway corrections can be done on the basis of the instrumentation data. Some corrections in the design or some construction technology, construction technique, or construction methodology also. So this can be used as for a quality control to ensure quality of the workmanship on a project, or you can assess the whether the work is being done as per our specifications or not. So of course, the safety of the structure is most important. So the instrumentation can help us in issuing the safety warnings at appropriate times. Because of course the legal protection is there. So after any failure or any distress, so those things are to be taken and deliberated by the examination committees or many other things. Performance, long-term durability, and stability of the structure is most important. So instrumentation should continue right into the operation and maintenance stage also. This should not be limited to the construction phase only. Some other objectives: monitor the effectiveness and protective or remedial measures which we do. So the efficacy of those remedial measures are to be assessed by the instrumentation. And then one more thing, to provide feedback to the client about the behavior and contractor on its performance. Documentation for assessing the damages to adjacent structures allegedly resulting from ground deformations. So it's not limited to your own structure. So it can affect the construction, or the excavations can affect the the buildings or the other structures in the close vicinity, and this instrumentation can help in protecting those nearby structures also, to advance the state of art by providing performance data to improve future designs. So we can the data from the instrumentation is sent back to the manufacturers also, so that they can the feedback from the on the performance of those instrumentation can be sent back to the manufacturers, and they can do some modifications in the designs or design of the instruments. Feedback to the industry for performance of instruments and technological upgradations through R&D. So in many ways, the instrumentation not only helps the project health and safety, but help the industry as a whole. So type of instruments, it can be mechanical, electrical, optical, pneumatical. So I'll not say which one is more preferable, but each one of these types can be utilized in different kind of situations. But one has to specify what kind of instrument for their own structure will be more beneficial. So the observations, regarding the observations also, those can be done remotely or at the or near the sensors, or those can be the signal can be transmitted through rod. So many things are there, through a liquid column or electrical optical cable. So those technological advances are already there. So planning and design of instrumentation. So first and foremost thing is, so you have to define the geotechnical questions. So what kind of information, what kind of parameter you want to monitor for a particular structure, and what will be their range and accuracies also. Select the parameter desired for the design, and then define critical values. Critical values means what are the permissible values? What are the permissible values? And what are the critical locations for instruments where the instruments can be installed? For example, if I talk about the concrete gravity dams, the deepest block has to be taken into consideration for maximum number of instruments. Predict the mechanism that control the behavior of foundation medium, and then a baseline magnitudes for each parameter, accuracy and range. Those are the things which I will be talking later in this presentation. Types of instruments, their benefits and limitations should also be known to the designers and to the dam owners. So this is the complete chart, how we flow chart which can be followed in case of instrumentation. So coming on to the first thing, the instrumentation for displacement, load, deformation, convergence, any parameter, or the water pressure, inclination. So you decide upon it and then design and specify the instruments. Then construction, monitoring and control, their design, verification and control, treatment control, and contractors' method of statements, then third-party approvals, installation, commissioning, and baseline readings have to be defined. Then you obtain and process the data. After installation of instruments, you obtain some data and then you process the data. So that data, then progress report has to be sent to the parties. So from that data might be within the limits. If it is within the safe limits, then you straightway report it to them. If suppose the measured data or the parameters, those exceed the trigger values or the permissible values, or rate of change of any parameter is quite high, then you have to again do some brainstorming, then assess the instrument first. Performance, you just have to go to the instruments to have to assess the instrument whether that measured data is correct or not. If the instrument is functioning correctly, then you straightway go for some remedial measures or some modifications in design. Suppose the instrumentation is not functioning correctly, then you need to compare it with some other instruments also, then repair or calibrate the instrument or install some new instruments. That has to be defined. So this way we can prepare a flow chart for each and every project stating the desired parameters. And hello, somebody is online. So coming on to the complete process of instrumentation. So I'll not start from the data recording or data processing. It is a process which starts from the production itself. So while production of instruments in the, I think somebody is unmuted. Please mute yourself. Dasam, please, somebody is still speaking. Yeah, please mute them. Yeah. So coming on to the process of instrumentation, so it starts with the production itself. From the manufacturing unit itself, the instruments are fabricated or produced in the industry or the factory, and then those are tested and calibrated. Calibration is the most important thing. That is the first thing which tells us the performance of the instrument. Then after that calibration, then packing and transportation to the project site, then storage at the project site itself. So it has to be properly stored as per the specifications. Then installation procedure, initial preparation of the instrument at site before the installation or initial monitoring or the base observation are the important. Base observations, why this is important? So that later observations are totally based upon the base observation. Protection from the construction activities, those are to be protected from the vandalism. Monitoring and comparison or verification of data with the previous observations as well as with the adjacent instruments. Why is say adjacent instruments? So because sometimes if you see some abrupt changes in the observations, then you need to compare it with the adjacent instruments or some other parameters also. So that you are confident that the data is correct and for correctness of the data. So data record management has to be there, data analysis, interpretation, or change of or variation. These can be cumulative or the rate of change can be there. Sometimes periodical changes can also be taken into consideration, seasonal or linked with some events also. Suppose we are doing some underground excavations, so the change in deformation or the loads can be on account of the benching down or some other activities or the blasting in the nearby vicinity also. Comparison or the predicted values, and then issues, advisories based upon the analysis, corrective, remedial measures, and then performance of the. So there are the different stages of instrumentation during design or tender stage. We have to during the tender stage we have to plan the factors affecting the data, then assign design, construction, and operational phases, tasks for that, select instruments, finalize instruments, and then write specifications, and then you plan installation, monitoring also. During the tender stage itself, you define the process, how you will be doing the instrumentation and what will be the terms of the tender document itself. While writing the contractual arrangements, you have to take care of all these factors. Sometimes you need to prepare a budget, then update the budget also. So mind it, every instrument on a project should be selected and placed to assist in answering a specific question. Suppose there is no question, then there will be no instrumentation. So design stage, you again identify the problems, identify the desired parameters, planning of instruments, then identify the suitable equipment, suitable locations. So assign responsibilities. During the design stage itself, you assign the responsibilities, how the data will be monitored and how the data will be analyzed and reported. One thing is there, during design stage, we can visit the manufacturing plant also. So we can have some information about the technical, for finalization of the technical specifications, that may be helpful. In construction stage also, so because apart from the, now we have decided about the instrument, their specifications and their process of installation and other things have been defined. But now the monitoring, the installation and the monitoring is more important. So the monitoring has to be done by the agency or by the owner itself. That needs to be defined. Suppose the developer doesn't have the adequate capacity, then we can have a inbuilt parameter in the contract so that we can have the persons from the manufacturing agency or the vendor for installation and monitoring of the instruments also. So those each and every instrument has to be provided a tag number, a particular tag number. That is more important so that mismatch is not there. Monitoring and reporting, analysis, all those things, and then finally documentation for future references. All the instrumented data or the experiences has to be documented for future reference and for help to the other projects. So operation and maintenance stage, of course, after the completion, so we extend the cables to the control room, and then we install the data acquisition system. Then again, protection of cables and the instruments, so those have to be taken care. Monitoring schedule has to be maintained at each and every stage during construction and during operational stage. So that monitoring schedule can be different for different kind of instruments or different kind of parameters, and or at for different locations also. Analysis and interpretation data to be continued. Any irregular, abnormal data needs to be checked, verified, and reported. Here, time is more important. Each and everything has to be do in a fixed time frame. So mitigative measures during operation stage can also continue. So these are the main phases of instrumentation and dam: pre-construction, construction phase, and first filling is more important in case of our dams, particularly in earthen embankment dams. And the filling, one should follow the filling manual completely without fail. Otherwise, the situations like Grada Dam may occur. Indicate first reservoir filling. In the first reservoir filling, this indicates early unusual behavior. Early unusual behavior, when I say the kind of development of pore pressures in earthen dams or the uplift pressures in concrete gravity dams, dam deflections. So those things have to be monitored for satisfactory performance of the structure. Then understanding actual response. Some new monitoring parameters, points, components may be required. Maybe suppose maybe some instruments may be required on the dam abutments also during that period. So those things continue. So during operational stage also, performance monitoring should continue. Actual behavior with design assumptions. Some parameters may not be required to monitor further. So for that, we can redefine the frequency of monitoring. So coming into back to the selection of instruments. So first thing is the range. Maximum limit. Yes. So the live coming back to the reliability of the instruments. First thing is the range of the instrument. We have to fix a maximum limit over which the instruments can be measurements can be performed. But the second thing is resolution, the smallest numerical range an instrument can measure. These two things are interdependent. If we increase the range, then definitely we will be losing on resolution. If we refine the resolution, then we might be losing on the range. So these two things have to be done in consonance with each other. So accuracy, degree of correctness with respect to the true value, that has to be ensured. The precision, repeatability. Suppose I repeat the observation 3 or 4 times, so there should not be that the change should be insignificant in that. That's at each and every time. So that the same observations will be there. That precision should be there. All these instruments should conform to certain standards, codes, or the contractual or the legal obligations. Robustness, proper functioning in harsh conditions. So that instrument has to be designed in for such conditions. Longevity, So these instruments are not being installed for 1 or 2 years or during the construction stage. So we take it into the operational stage also. So longevity of these instruments should also be there. Of course, ease of installation, maintenance, and automation should be on priority. One thing, let us understand, poor quality or inaccurate data can be misleading and is worse than no data. No data is better than the poor quality or the inferior quality of data. So some principles of good measurements. Hello? Somebody is unmuted. Yeah, please mute him. Yeah. So some good principles: make the right measurement, choose a right instrument, right pupil, demonstrable consistency, and regular review, and right measurement procedures. One should not go by the shortcuts. So these are some of the common problems in instrumentation. Sometimes instruments do not work, and sometimes these are not protected, and vandalism is there. Some wrong selection of instruments can also be there. Lack of coordination between instrumentation and civil construction agencies. Sometimes we select too sophisticated instruments which may not be needed. Reliability, reproducibility, correlation. These are some of the factors that affect the data. Inaccurate measurements, inferior measurements, selection of wrong instruments, improper locations also. So improper installation, delayed monitoring, and other things. These are the things which affect the quality of data. So presentation of data, when I come on to the presentation of data, many times we present the data in the tabular forms, which is not a good practice. To me, graphical presentation is the best method. So in graphical presentation, we need to know the earlier observation, so we can have a look at the earlier observation and the current observation all together, plotted from since the installation of the instrument. So we can have the different the assessment of or the performance of the structure in various phases of construction. And then in graphical presentation also, there are two ways of presentation. One is the cumulative kind of change in any parameter, and the other one is rate of change in any parameters. Those have to be, both these the graphical presentation should include both the cumulative as well as the rate of change. Observations to be compared with the other instruments, construction activities, or the observed trends to be compared with predicted trends. Key designers to be involved and kept informed all the time. The data should be shared with the designers, with the construction agency as well. So trigger values, measurement must be part of risk management process. So we need to define the trigger values. Usually designers define the permissible values or the maximum trigger values or the warning values, the signals, and each and every instrument has to be provided with these trigger values. So at what change in any parameters, so we will say that this is within safe limits, or some warning is there, or some alert values have already achieved, and this is the time for action. So we need to define these flag indicators for each and every instrument. We can do it. So this can be done. It's not a big thing, but this should be followed. So setting the trigger values. So observed variation in any parameter falls within the expected limits. That's the baseline level. So warning level, when it exceeds the baseline level, alarm exceeds the warning level. Example, let us take the example of a load cell. It's an example, but designers may define some different values. So just for the purpose of explanation, the trigger values, suppose we are installing a load cell on any rock bolt, then the baseline value which we may define as if it doesn't exceed 50% of the yield capacity, then we can say it is within safe. Or warning, it exceeds 50% of the yield capacity of the vault, we can say we can issue some warning signal. And then alarm or alert values, then load surpasses 62.5% or 70% whatsoever of the yield capacity, then we can say, though now it has exceeded that, now it's a time for action and time to define the causes of this kind of distress or this kind of increase in load. So one has to take the remedial measures. Similarly, settlements in an earthen dam, normally we define that 1% of the height of the dam, the settlements can be there. That's a maximum settlement, but depending upon the kind of material, so those can be lesser than that also. But during the instrumentation, you can regularly keep a watch on these dam deflections and other things. So those values needs to be defined at this stage. Frequency of monitoring can be dependent upon hazard potential, age or condition of the dam, variation in loading conditions, history or abnormal behavior, or seismic risk, phases in different phases, nature of data, climatic variations or some seasonal variations, or this can depend here. Timelines are very much important in instrumentation installation. Timelines for installation, monitoring schedule, reporting, passing on the information to the concerned, and then making decisions. These timelines at each and every level has to be followed. So good practice, I think I have already covered. This is one part is over now. So now I will switch over to the case studies. We will discuss the case studies. अच्छा यही है ना? Okay. Okay, so coming on to the second part, implementation of instrumentation. So in this part, I will be covering instrumentation for a complete project. So I was there on deputation to Tala hydroelectric project in Bhutan. So we were associated with instrumentation of the dam, underground structures like desilting chamber, HRT, powerhouse, and all. Apart from quality control and quality assurance, we were responsible for instrumentation of the complete project also. So I'll share that case study with all of you. So apart from that, I'll share some other case studies also of earthen dams as well as some underground structures also. I'll try to cover the. So coming on to the dams in different phases, I've already told that this is so concrete gravity dams. Before I go to the case studies, so let us understand the different modes of failure in concrete or masonry dams. The common causes are overtopping that might occur due to inadequate spillway capacity or some issues with the gate. Sometimes the gates get stuck or something, we are not able to lift those gates or something. So that may also be one of the reasons for failure or for overtopping. And then spillway blockage resulting in erosion or of the foundation or at the toe or even on the abutments also, washout of abutment. Overturning, the dam can fail by overturning. So this is a result of high stresses at toe. Then foundation leakage is one of the another factor or the causes of failure in concrete or masonry dams. Sliding along weak discontinuities in foundation. That's why we carry out the in situ investigations for shear strength of foundation in both rock to rock interface as well as concrete to rock interface. Or sometimes failure of upstream or the downstream slopes of the embankment also, this may cause failure of the dam also. These are the common causes of failure in concrete and masonry dams. Now I'll straightway go to Tala hydroelectric project case study. So this is Tala hydroelectric project in Bhutan. It's a 1020 megawatt hydroelectric project under operation right now. So the project was under construction from 1997 to 2006, and the first unit was commissioned in 2006. It's a 92. It contains 92-meter high concrete gravity dam. So extensive instrumentation has been taken in this dam, and of course, our Central Water Commission was the main designer in our Tala hydroelectric project. Installed capacity is 1020 megawatt, and the gross head. This is 860-meter head is there. This is a gross head to which the turbine units have been subjected. Contains 6 units, 3 underground desilting chambers are there, and 23.2 kilometer long head race tunnel is there, 6.8 meter diameter, RCC lined mainly, but some of the sections are PCC lined also. Contains surge shaft and 4 number of steel lined pressure shafts, each measuring more than 1 kilometer in length, and then underground powerhouse and transformer hall, cavern, and of course tail race tunnel. So these are the kind of instruments which have been installed in our dam. First I will cover dam, then I'll straightway go to the underground structures. So temperature meters have been there, pore pressure meters have been there for measuring the pore pressure of the foundation, and then uplift pressure meters are there, joint meters, crack meters at the block joints, multi-point borer sensometers in the dam galleries, on the abutments, normal plumb line, inverted plumb lines are there, stress meters, strain meters, strong motion accelerographs have also been there, automatic water level recorders, seepage monitoring, and of course load cells in abutment galleries. These are the kind of instruments which have been installed there. This is the key feature of the contract. Why? Because so this is the key, case study of a successful project, successful instrumentation. So how this could have been made successful? Some of the key features I would like to share with you. Because normally what we do in our contract for instrumentation, we make it a part or the subset of the civil contract. Civil contract, this means the instrumentation work is also awarded alongside the civil contract, and the agency responsible for the construction is also responsible for installation and monitoring of the instruments also. So that is not a good practice, because on one side the tendency of the agency will be to give a higher or very faster progress, and on the other hand the installation of the instruments may hamper or may retard the progress of construction. So here at Tala we included the supply, installation, and monitoring of the instruments in the contract. It was embedded part of the contract, and for that we one clause was there that the agency has to depute a certified or a experienced civil engineer or to at the project site who will be responsible for preparation, installation of the instruments, and as well as the monitoring of the data, and the salary of that person along with the one help will be paid by the authority, the Tala Hydroelectric Project Authority, every month. And pre-dispatch of inspection was included in the contract document, and calibration was done, was witnessed by the quality control team. Every time the instruments were to be dispatched to the project site from Lucknow. So and Cardiorite was the agency there, given the contract, and that every time we used to come to Lucknow for inspection, pre-dispatch inspection, as well as to witness the calibration of the instruments. Then monitoring with monthly report submissions. The person who was stationed there from the agency, he used to monitor the instruments and submit the monthly reports of the instruments. So monthly reporting of monitor data with graphical presentation by the firm to QA QC unit was a regular feature. And monitoring charges for manpower included, I have already told. And then responsibilities of handling contract was assigned to QA QC rather than the construction agency itself. So we handled that contract. The QA QC team handled that contract, and then reporting was directly to the top management, not to any EIC construction or other. We were directly reporting to the managing director, and through the managing director, all the observations or the interpretation, those were being forwarded to the EICs. One thing I will like to add on here, over here, some disturbance is there, yes. One thing I will like to add on over here, that the agency was, the bills were being processed only after confirming that the instruments have been installed satisfactorily, and those are giving some meaningful data and being monitored. So then only we were processing those bills of the firm. These are the initiatives, and for some other initiatives, resonance or coordinates with the construction team, or protection from the construction activities, remedial measures undertaken if felt necessary. So those are the things, and discussions during monthly progress review meetings. Every month we used to have the PRM, progress review meetings, taken by the managing director alongside all the EICs, and those instrumentation data was also being discussed and deliberated in the meetings. So these are the kind of instruments which have been installed. Around 200 out of 296 instruments proposed initially, 277 instruments have been installed, and out of which, when we left in 2006 after completing our deputation period, so out of 277 instruments, 272 instruments were working perfectly and giving very useful data. That is the successful story of instrumentation of Tala Dam. So 2 blocks were chosen for dam instrumentation. One is block 2, which is a non-overflow block, and the other one is block 5, that is the overflow block. But somebody is talking, I think. Let us mute, or kindly mute yourself. Yeah. Some voice is coming. Yeah. Can you mute yourself, please? Hello? Somebody is talking. Yeah, please mute yourself.
Hardev sir, please go ahead.
Some actually regular voice is coming. Yeah. Yeah, it's quite loud. Yeah.
Yeah, please. Just a minute.
Some disturbances there. Can you mute it? Yeah.
Yes, all are requested. Please, mute yourself. Please mute yourself.
Okay, so I'll continue. So 2 blocks were, as I have already told, 2 blocks were chosen for maximum number of installation of instruments. Block 2 being the non-overflow block, and block 5 being the overflow block. So these include the instruments like uplift pressure meters, and then port pressure meters, and then the stress and strain meters are there, temperature meters are there, normal plumb line, inverted plumb line is there, So all kind of instrument, joint meters, so all kind of crack meters were also wherever we observed some cracks. So all those instruments were included there. So coming on to one by one, temperature meters. So temperature meters, so these have got a very good significance and importance in our concrete gravity dam. So in Tala project, the cement in mass concrete, it was varied from 200 kg per cubic meter to 140 kg per cubic meter. But that was not changed abruptly. So we initially 200 kg per cubic meter cement content was specified and in dam in mass concrete, but later on we observed that lesser the quantity of cement in mass concrete, so lesser will be the thermal stresses, and it will amount to a negligible or no cracking in concrete. Yeah. So we monitored regularly the performance of each and every mix. Then in stages from 200 to 190, 180, then 170, 160, and the minimum quantity of cement used is 100 kg, 140 kg per cubic meter. So the temperature of mass concrete maintained at the batching plant was 10 degrees centigrade to so that to avoid the heat of hydration to be under control. All 51 temperature meters were installed in block 2 and 5 at different elevations in the block. And then temperature variation due to heat of hydration was of the order of 8.6 to 30.9 degrees centigrade. But usually what we do, we install that temperature meter, and then we start monitoring from the next day or some with some time delay. So we can do one thing here. I would like to suggest one thing. After installation of the instrument itself and placing of concrete, one should start the instrumentation during the early stages. When I say the early stages, it is within the first few hours of concreting itself. From there, you will see how the heat of hydration changes. So that heat of hydration accounts for the thermal stresses, building of thermal stresses in the dam. So in the table, if you see, I have marked two sections, two blocks, two rectangles or squares, something like this. So the maximum temperature which we observed was of the order of 30 or 31 degrees after placing the concrete. But that was when the cement content was of the order of 200 kg per cubic meter. When we reduce it to 140, you can say the maximum temperature was of the order of 13, 14 degree at 50 or 16 degree itself. So this way you can control the effects of heat of hydration in our mass concrete. This is very much important. In mass concrete, the strength is not important. The important is the heat of hydration, which can amount to the cracking in concrete. So we should keep the cement content to an optimal value in our mass concrete. It's not necessary that you go for higher quantity of cement. And second thing is, instead of using the OPC, we can use the other kind of cement like Portland slag cement or PPC also. So because some part of the cement is replaced with some pozzolanas or some fly ash and other things, so to prevent to lower the heat of hydration. So we can use low heat cement also in mass concrete. So these are the plots of temperature meters. So during construction phase, these are very much important. So the data from the temperature meters can be utilized to schedule our concreting schedule. to plan our concreting schedule. So once the temperatures are after the heat of hydration, the temperature of the concrete normalize, then we can go for the next lift of concrete. Yeah. So you can plot the variation in ambient temperature also, the pore pressures also within the foundation. You can monitor the pore pressure during the construction phase, but the first filling is more important here. Joint or crack width also, every time you can continuously monitor. So at the block joints, these joint meters are installed to see any movement along the axis or across the axis. Some minor movements have been witnessed over here of the order of around 0.5 millimeter or so. Those are quite negligible kind of changes or variation in joint thickness. So multi-point bore sensorimeters have been installed in the abutment galleries. Although the proposed were 9, but only 3 could be installed there. And from those MPVX, the data indicates the maximum movement of the order of, I think, 0.6 or 0.8 or 9 something, 0.9 mm. 0.9 mm is very quite negligible kind of deformation which we could get in from the MPVX. Normal and inverted plumb line were in place. And one thing I would like to say over here, so while installation of this normal plumb line, this is the last instrument, some of the last instruments which are installed in concrete gravity dam. So, but this should be in place before the first filling. Only then you will be able to know the effect of reservoir level on the dam deflections. Yeah, dam deflections are related to the reservoir filling. So before the first filling, these normal as well as the inverted plumb line should be in place. So here, before the first filling, which was taken up around December 2005, then these plumb lines were installed, and then monitoring was started in the first filling. If we see the maximum kind of deflection, it is around 8 or 9 millimeter or so from the normal plumb line in block 2, which is non-overflow block, and in the overflow block it is of the order of, or I think from the inverted plumb line in block 5, it is of the order of 0.5 millimeter in the foundation. Yeah. So both these deflections are within the permissible values within as expected. So strain meters and stress meters are installed all together in closer vicinity. So strain meters are normally provided in the rosette kind of configuration, which I have already shown over here in the picture. You can see the second picture is I think I have on has been zoomed in to have a view of the strain meters, how these look like. Yeah. So it contains 5 strain meters which measure the strains, and one strain gauge is installed in a chamber like this, in the rubberized chamber or something plastic chamber, so that it is not stressed. Rather, it is called no stress no strain meter. So it contains, so rosette contains 6 strain gauges, including one no stress no strain gauge. And in Tala, we installed 21 sets of strain gauges. 126 strain gauges were installed there. And in this these strain gauges have been installed in angular positions. Of course, those can vary depending upon the structure also, but this configuration has been utilized in Tala. So vertical strains from the first 11 strain meters showed the variation from 13.8. This is the kind of parameters or the kind of statistics. But how can these strains help us in assessing the performance of the structure or the safety of the structure? These strains can be utilized to work out the stress at any particular location, assuming the modulus of the concrete, or another way you can get it evaluated. The modulus of the concrete can be calculated or determined in the by casting the cylinders or the cubes, and then tested those cylinders in the lab. So from there we can calculate or determine the modulus of elasticity of the concrete, and then strains are already there, then you can work out the stresses. And from there you can have a confidence that our instrument is working all right and the performance of our structure is satisfactory, because the stress meters, these are the kind of strains, but the data from those strain meters, quite consistent data we got. These are the stresses in mass concrete. So stress meters are also installed alongside the strain meters. Why? Because these two terms are quite, but they are interdependent, and we can compare the strains as well as the stresses also. From stresses you can work out the strains, and from strains you can work out the stresses also. So this way you can verify the data also. So here the stress variation was of the order of 3.8 to 5.5 kg per square centimeter in block 2, and in block it was of the order of 4.4 kg maximum. So theoretically, we have worked out from the weight of concrete itself. So those blocks, those are quite high theoretical stresses. So the measured kind of stresses are well within the feasible or the permissible values. Uplift pressure meters are tells us about the pressures at the foundation, acting on the interface of the dam with the foundation material. So these were installed in both the blocks, block 2 and block 5, and from that data, during the first filling itself, we could monitor the uplift pressures, and the maximum pressure was of the order of 12.5 meter water column. So well within the permissible values, and from there you can draw uplift pressure diagram also, following the IS code also. 4 strong motion accelerographs were also installed after the commissioning of the dam, one in the bottom gallery, one at the top of the dam, and 2 strong motion accelerographs, one on the left abutment, other one on the right abutment, were also installed, and automatic water level recorder, you can you can install it and place it, which can continuously monitor the recorded or record the levels. Now coming on to, this is the case history of the dam which we undertook, and so this is of course a successful story, I can say, but way back in 2006. Later on, what is happening? So we have not got no information about that. But up till the commissioning of the dam, those instruments were in working condition. So coming on to the underground structure monitoring. So those structures can be cut and fill type structure, wherein stresses in struts or anchors or deformations of the adjacent ground or the buildings, those kind of parameters can be undertaken, which requires strain gauges, tilt meters, total pressure cells, convergence meter, load cells, Inclinometers also to monitor the movements of the subsurface. Borehole extensometers can also be installed. On the surface structures also, some of the instruments like tilt meters can be installed. Or even in such situations, vibration monitoring on account of the machinery or some other excavation process can also be monitored on the nearby structures also. So in shallow depths also, even this kind of instrumentation program can be considered, which includes again similar kind of instruments as in cut and cover. And then in deep tunnels, so we are concerned with the tunnel and its surrounding itself. So surface, we assume that the tunnel is quite deep and the surface structures are not affected by the excavation of our tunnel. So here we usually specify the instruments like MPVX all around the adjacent or the periphery of the tunnel surface, and then we can provide these optical targets, and depending upon the shape and size of the tunnel or the cavern, so those can be 3-point or those can be 5-point measurements can be there. So in addition, we can have some load cells on the rock bolts, load cells on the steel ribs if any, and some piezometers to monitor the water pressure or the seepage pressure in the rock. So the Tala project had 3 desilting chambers of two sizes of 250 by around 14 meter by 19 meter size, and the hopper shape structure on the right side topmost figure you can see. So this is the kind of after excavation the structure looks like this. And later on what happened and this is the on the left side of this, you can see the photograph after completion of the chambers. We usually do inspection of all the chambers, but our team comprising the project and the designers and quality control, QA, QC, and so all those involved, including the construction agency. So we take up the inspection of all the works before put into service. So all those chambers were inspected before filling for first operation. So what happened actually on the right hand side on the figure which you are seeing, again it's in filled condition, and in the crown you can see some certain changes in support rock supports. Initially we thought the designers designed it as a rock bolt supported crown arch, but later on what happened on the basis of the instrumentation data, so some problems occurred. So then design review was taken, and again these chambers were filled with muck, and those design reviews were implemented. Like the crown arch was designed as steel rib support arch, and those changes were incorporated in execution. So how this instrumentation can be planned in chambers like this? So we can again look the similar kind of instruments. Multi-point borehole sensometers can be there, load cells can be there, surface targets can be there, piezometers can be there. Why that was taken? At one of the RDs, the maximum change or the deformation was of the order of 122 millimeter, and which was and visually also what we saw that some cracks in the shotcrete lining appeared at those places, and in the MPVX observations we could get maximum deformation of the order of 122 millimeter, and because of this stress conditions in the desilting chambers, the design review was taken, and those steel rib arch support was provided there. So displacements, you can plot it like this also. These can be related to excavation stages, including the first benching, second benching, third benching. So you can plot these deformations and assess the performance of this structure. So this is the continuous kind of graph from since its installation. So convergence of concrete. Just see concrete wall from installation till completion, till you continue the monitoring. So this has to be continuous. Yeah, like this. So at different RDs and different elevations, so instruments installed can be plotted. Yeah. So ultimately, you can have a summary of the uh, observations of this. This can be done. So HRT is, it's a 20, as I told, it's a 23.03 kilometer almost, but later on as executed it is 23.032 kilometer in length, and diameter is 6.8 meter finished dia, and excavated dia is 7.8 meter, and some of the reaches wherein we witnessed very poor or very weak kind of geological mass, the diameter has been reduced to 6 meter also, 6.3 to 6 meter also. So excavation has been done from 11 phases, and around 290 meter length of the HRT was excavated in very poor squeezing ground conditions. So I'll a little bit I'll tell you about that particular section. So I will be concentrating on that particular section. So this is the plan of HRT, starting from the dam to the powerhouse. And it has been, as I have already told, it has been excavated from 11 phases. But here, where bypass of HRT is there, this part was excavated in very poor ground conditions. When I say very poor ground conditions, it's basically soil-like materials, very squeezing-like materials with water ingress. Why we need instrumentation in underground tunnels? Because during the initial stages of project, during DPR or the initial execution stages, we cannot, many a times we cannot have comprehensive geological or geotechnical investigation all along the alignment of the tunnel. So on the basis of certain outcrops, we project those outcrops downwards through the subsurface, and then we uh, estimate or anticipate the rock mass conditions down below at the level of the tunnel. But when you execute it, the things might be quite different, as evident from this figure itself. You can see just the class 1 rock, how much percentage was expected and how much we could actually get. 4.7% was anticipated and 0.03% was obtained. Even in class 2 also similar kind of situation, and class 3 also, class 4. And when we go to class 4, so the kind of variation, just see the deviation from the anticipated and the actual ground conditions. And these are final two ground conditions were not anticipated, but those were encountered. So this is the finished line HRT. But this looks like this. And this is a schematic diagram of instrumented section in HRT. Again, similar things: piezometers, optical targets, MPVX, load cells. And the section which I was talking about, the typical squeezing conditions in 298 meter, which has been overcome by dress technology through forepoling and then support system installation. So this was the kind of conditions in the very poor ground conditions. So all those methods were worked out, so multiple drifting method, and even polyurethane supporting was also attempted. 4 poles were attempted, even so both all those things, microfine cement grouting was attempted. So all those things were tried, but we could not that uh, make that structure stable. But ultimately, a collapse occurred, and around 70-meter tunnel collapsed with mud, and fortunately there was no casualty. So this is the kind of instrument situation, and that the face was, after that the face was plugged and then diverted. The tunnel line was diverted or detoured from the original alignment, and then again similar conditions we witnessed. But this time we were fully prepared to tackle these conditions, and then we went for four-poling machine, and that machine was there, and then we installed all the four poles, and then took up the construction activity, and treatment was done. And instrumentation was extensive. Instrumentation was undertaken in this particular section. As excavation was being done from the two faces, one from Virchingchu downstream, another one from Kalikula, from two faces, we were approaching this shear zone, or the very weak kind of squeezing ground conditions. So maximum load, you can see 173 ton on one of the ribs was recorded over here. 22 sections in around 300-meter length of the tunnel was monitored. When I say 22 sections, those include the load cells, those include the optical targets, those include the piezometers. These are the three main kind of instruments which have been installed over there. Just see the different sections from one face and the maximum load. So although it increased, but later on this the stabilization was witnessed, was observed. The loads gets stabilized after certain period of time. In underground tunnel, one should apply the final lining after the loads and the deformations have already stabilized. So the final lining was undertaken after stabilization of the rock loads as well as the deformations or convergences. So loads on ribs, these are the kind of graphs you can say. So one should be prepared to analyze the data in such a manner so that it is quite easy for understanding. So again, some of the instruments on the load on the ribs, and then convergence measurements. Just imagine how much convergence, 463 millimeter also we witnessed. I'll show you with some here also. Just see this figure. 463 millimeter deformation, the convergence was observed at one section, that is around 1139 meter. So to confirm this convergence, we installed another target just within 2-meter vicinity, and this 211 deformation was recorded there. So similar kind of observations were there. Similar kind of trends were noticed just adjacent to this location. So that's why you need to have a comprehensive look, and sometimes you book some very the instrument showing some very abrupt or very abnormal behavior needs to be confirmed also. So this way we monitored this very vulnerable, very critical zone, and that helped in scheduling our concreting schedule after the deformations and loads were stabilized. But another thing happened over here. We monitored it, and then these are the rate of change of deformation also. You can see the rate of change at two different periods. In January, the upper one graph is during January, the down one is during September. You can see the rate of change of convergence has reduced to very negligible kind of levels. So that from there we can say that deformations or that convergences have stabilized, and now we can go for the final lining. So this way the instrumentation helps us in scheduling our construction activities. So actually, again, what happened when we were about to start the lining itself, then we removed the muck from the invert, then we witnessed one strange thing. These uh, broken bottom studs, because it was a closed section. The bottom studs were broken like a piece of paper. You can see how much deviation or how much deformation it has occurred, around 450 millimeters. So it has been torn like piece of paper. So then we rectified those invert studs also before placing the concrete. And this is the upheaval that was also monitored and calculated the upheaval from the invert also. So this way, so then this is the modifications or rectification measures in the steel ribs. Inverts have been closed, and the new studs have been provided like this. Those have been welded to the posts. And finally, lining was also an issue. So because in this section, the two rows of reinforcement of 32 millimeter diameter and at spacing of 75 millimeter center to center, that was defined in the design. And to place that concrete in very harsh conditions of reinforcement, it's a big challenge. It was a big challenge. Then we designed self-compacting concrete for this section, which requires minimum vibrations, so to fill the gaps. In underground structure also, in powerhouse also, we monitored different sections at different elevations like this. This is the kind of this is the sketch showing the powerhouse cavern and the underground cavern and bus ducts or the tailless tunnel. And then these are the sections 1580, 130, 150 millimeter. These are the sections which have been monitored extensively. Again, MPVX at center of the crown, on the left and right side of the crown, anchor load cells on ribs, pore pressures, and convergence monitoring. So all those instruments have been installed there. So you can just see, this is the plan showing the instruments installed in the powerhouse. So again, loads were monitored, and all these. This is the data from the load cells. And again, you can see this shown in the graphical presentation on the downstream wall as well as on the upstream wall. So the loads of the order 135 tons were recorded, and some of the rock bolts were observed to be failed also. And this is again load on ribs at different sections, loads on rocks at different sections again. So this kind of maximum load. This is the radish I think one entry 43 tons we are seeing. These rock bolts, these are the anchored rock bolts that failed during the excavation or the construction process. Because these are the load observations. Maximum load on the rock bolts was of the order of 43-45 tons. And again, convergence. Coming on to the convergence in powerhouse walls, 343 millimeter maximum convergence of wall was observed at RD 65 meter. So this is quite high observed, and this was continuing at that point of time. So to counter this, some design intervention was also undertaken by the designers. So initially we planned the concrete columns for resting the EOT crane. but later on we transferred to the steel columns, keeping some space in between the rock and the column for future convergences, if any. So those design interventions were helped in design reviews also. These instrumentation data was helpful. So these are the convergences. You can see the maximum kind of conversion 343 millimeter. So monthly convergence rate was plotted again. So even here also, while concreting for the uh, uh, machines, generating machines, some cracks were noticed. Floor upheaval was witnessed, and that floor upheaval was also monitored using those the using the MPVX installed in those bits. And once those convergences, those upheaval process has settled or stabilized, then we went for the installation of machines in all the sections, all the units. So this is the kind of after additional support measures. Our additional support measures included some additional rows of rock bolts, including the self-anchored Maya anchors or DVX map anchors, something. And then no displacement was observed beyond 1 meter in all the MPVX. Total station targets in pits we installed. But all these measures we could monitor, and we could implement the design in a very efficient way. Another study of Vyasi Dam, here we were involved in, this is the case study of basically Tala project, which included the dam, the underground structures. So very extensive instrumentation has been undertaken, and that helped in project execution and improving our design also. So now I have got another case study of Vyasi Dam. So Vyasi Dam, it was put into operation in 2021. Have you got the time? It's 2023. So I think with 10-20 minutes more, I think I will finish here. So these are the kind of instruments which have been installed, and we were involved during the first filling stage. These are the different blocks which have been monitored: block 4, 8, and 12. Block 8 is the deepest block and is the overflow block, and this is the surface powerhouse. And on the back slope of the powerhouse, the slope stabilization measures have been undertaken, and on the slope some instruments like load cells, inclinometers, and then piezometers, those have been installed there, and those are being monitored remotely. So using the solar batteries have been provided for at the junction boxes, and this is the kind of flow chart of geotechnical instruments in on the hill slope itself. Just see some of the pictures showing the load cells as well as those junction boxes, which are connected to the system remotely, and we monitor in our control room without extending any cables there. So during the first filling, we observed some of the things in this slope stability, which I wanted to show it to you. During the first filling, the water conveyance system gets charged. When the water conveyance system gets charged, then some changes in the adjacent rock takes place because of the seepage problem, or because of the saturation of the ground. So we, from the monitored data itself, we could observe that some changes in loads, some changes in these are the changes in loads that occurred during that period. So some changes had occurred, but those changes were change in loads were quite minimal, not very not very significant. Again, in case of this inclinometers, also some changes we witnessed, but those were quite minimal. So from there, you will get confidence that your instruments are working properly and your structure safety is ensured. So earthen dams, so everybody knows about the failures of the patterns and causes of failures in earthen dams, maybe due to overtopping, maybe due to piping, maybe due to failure of downstream, upstream slope, maybe due to sloughing, maybe due to rain cuts, or maybe due to some other factors, piping, maybe there, or structural failure, maybe there, upstream or downstream slopes can fail. But these are the kind of early indicators of failures. Excessive settlement may be one of the reason. Increased seepage or turbidity could indicate piping. Sand boiling on the downstream. Settlements of an embankment crest or inelastic movement of concrete structures. So at the junction of the structure, junction of the concrete structure with the earthen section, so those sections are vulnerable. Conversely, lack of normally expected natural phenomena may also be the factor. So those are the kind of early indicators of failure. These are the parameters to be monitored in earthen dams and concrete dams. I have listed all the parameters for earthen, concrete, earthen dams or the concrete dams. In earthen dams, we can have some water level or pressures or seepage or pressure, some pore pressure monitoring can be there. Of course, stress meters or the settlement devices can be there, temperature, seismic loads. All these similar kind of instruments can be installed. So coming on to the Tehri Dam, so it's the highest dam in India, 260-meter high dam. And it contains two inspection galleries also at the 725 and 830 meter. And this is the photograph of Tehri Dam. Something. This is the project photographs during construction phase. You can see the earthen clay core at the center and followed by the shell material. And these are the kind of instruments which have been installed: piezometers, vibrating wire, earth pressure cells, vibrating wire thermometers, deflection and settlement devices, full profile gauge, horizontal movement gauge or horizontal multi-point extensometers. So these are the kind of instruments. Three particular sections, B11, B7 and B15 have been chosen for instrumentation. And some of the instruments have been installed in the valley section and some of near the top embankment. And many of the instruments for surface settlements have been installed over there. These are the kind of parameters monitored: hydrostatic pressures, pore pressure, seepage measurements, deflection, internal vertical movement, opening of. This is one of the successful case study in India, if I say, for earthen embankment dams. Tehri Dam has a very good instrumentation plan and well executed plan. And these are the kind of instrument, the numbers, how many instruments have been planned. This is the footprints of the Tehri Dam, section B7, B11, and then B15. Of course, instruments in the valley section, location of inclinometers in the dam body itself, location of seepage monitoring devices, seeping measurement devices, and then this, just have a look at these surface settlement points. How many points are there which were monitored using the total station during construction on both the slopes, on the upstream slope as well as on the downstream slopes. Some of the photographs during installation of the instruments, and then horizontal displacement. But one or two things I'll like to. These are the installation of horizontal movement gauge, how these are installed. Full profile gauges, horizontal multiple point soil extensometers, cable. A data acquisition system has been installed there. So extensive instrumentation plan has been devised there and implemented in Tehri. So one case study is small, but I'll take just 2-3 minutes more. So I'll conclude. It's a diversion tunnel of Laghwar multi-purpose project. So which is presently under construction in that too in a very difficult or very varying ground conditions. because it contains one contact, lithological contact on the downstream and the upstream of the dam, well within the desilting basin, or the two penetrating into the dam body in the subsurface. So this project is, it's a 204-meter high concrete gravity dam under construction right now. So, but the project was started way back in 1990, and due to some uncertainties or some very weak shear zones or contact, lithological contact, that was abundant, and later on in 2003 it has been taken up for construction again. So the first thing was taken up the diversion tunnel of, although two of the diversion tunnels which were initially planned were executed and were completed, but now because of the construction of Vyasi Dam downstream and the changed conditions, so and because of those diversion tunnels were are filled with muck from the outlet side, and those cannot be utilized for further for diversion of river. So there are new tunnel, diversion tunnel 3 has been planned, and we were expecting are expecting that shear zone to be encountered, that lithological contact to be encountered somewhere around 250-meter RD from the outlet side. But because from the previous investigations, though we can project it on the tunnel alignment, we have projected it, and this is the kind of instrumentation. So here we went for the 5 optical targets only. 5-point optical targets have been planned and executed in this tunnel and being monitored regularly. This is the kind of shear zone which has occurred at the expected RD. But we are monitoring regularly at different RDs. This is the kind of sections which have been monitored, which are being monitored. This is of course, many more sections have been added onto it. This has to be updated. So this is again data is related to something details of the instruments. So these are the convergence movements that, as I have already told, there are two methods of presentation. One is you can plot on the upper graph, you will see that the cumulative deformations are there. On the bottom, you can see this rate of change of movement. So the first picture on the left side, you will see the rate of movement. This is related to the that particular nodal point where the target has been installed. On the right side, this is the convergence between 2 points. 2 points. So rate of change is also important. From this rate of change, you can say that whether the section has been stabilized or under stabilization, or it is still active. So from there you conclude, but not you for conclusion or for conclusive remarks, you need to plot the rate of change also. That is my observation. So just to show you how you will say the stabilization, whether it has stabilized or not. In the topmost picture, you will say that I am saying that it is an under stabilization process, because the deformations are plus minus 5 to 10 mm, but within limits. On the bottom also, the same has been plotted. So you can say that this is the under stabilization and still active, still showing some abrupt changes in deformations. So at the sections to be interpreted individually based upon the visual inspection we'll be doing, most important. So I'll say compare with the previous observations immediately, continue in data in graphical presentation, total deformation, convergence, and then rate of change of with time you can monitor and assess. Monitoring schedule you can prepare and go on modifying it. Final word, whether stabilized, under stabilization, active state, you have to define it. Minor verification in data should not be taken lightly. till it is for sure. Word of caution at critical stage. These are some of the typical examples how these plots are used for interpretation purpose. Just see, this is one of the the figures from one of the major projects in India of the underground structure, wherein an abrupt change in deformation in MPVX has occurred, and while deliberating or discussing, the cause of that change was also ascertained. So the variation of your normal plumb line with the change in reservoir levels. These are the some of the photographs of bad instrumentation. Where when you install V-notch, you should be care enough, and your junction boxes and your cables have to be protected. These are the kind of instrument later on after the commissioning you forget, and then the kind of the data acquisition system and other your instruments, those should those look like this here. So my concluding remarks, so finally I'll conclude. The instrumentation offers scientific and convenient tools for periodic inspection of structure. It facilitates verification of design assumption and adoption of timely and appropriate remedial measures to avoid aggravation of distress. Still unrecognized and instrument only when in stress. Consider hindrance in work progress. Installation timing and proper procedure has to be followed. The instrument should be simple but reliable. Before investing in technology, invest in people. Training or capacity building should be considered. And then some of the lessons: no instrumentation better than bad instrumentation. Data once lost is lost forever. Therefore, deformations in underground excavations had to be arrested or had to be recorded timely. Keep your eyes and ears open. Visual inspections serves as verification tool, even in case of malfunctioning of instruments. Small amount of true, accurate, reliable, and realistic data, far better than large amount of inaccurate and erroneous data. Consistency in monitoring data should be there. Proper identification of instruments and measuring units. Frequency of monitoring. Proper formats have to be used. Assigning responsibilities at various levels. Those are the kind of lessons which are the lessons learned from the previous monitoring and instrumentation. So with this, I end my presentation over here. Any sort of queries or any questions are most welcome.
So thank you, sir. Thank you, Hardev Saab. Thank you very much. Means you have very rightly elaborated all the these all the perspectives of this dam instrumentation. Actually, conclusion. I was just looking up to this, reading all the lines of the conclusion. Definitely, this will help a lot, because means after putting instruments means their analysis and timely remedial measures. First of all, their interpretation is very tough, very complex. It's not so easy. If instruments are not calibrated properly, then it gives the wrong signal also many times. So all these points are very important. And now floor is open to the all the participants. They can have a questions. Hardev sir will take it happily.
Sir,
Yeah,
Sir
please.
Harijan sir, Namaskar. This is Raghavendra Kumar Gupta, and just I want to ask you regarding the Tala. You had done very nice instrumentation and interpretation also. That timely installation of instrument and protection from the damage from the construction activity is very important. And how did you manage this protection and timely installation, and what was the lag in the excavation of the face and installation of the instrument? These are my two questions.
Okay, yes, sir. Thanks a lot, sir. Thanks a lot for your question. So at Tala, actually, because the responsibilities were fixed, responsibility of the firm which was assigned the task of installation, responsibility of the departmental division quality control and instrumentation which looked after the installation, which looked after the installation of instruments at proper locations, and then protections, it protecting it from the vendor construction activities through protection of the cables and other things. So those were taken care, and we were working in close resonance with the persons works division, so that no abnormal thing happens. And at the end of the construction phase, so those cables were extended to the control room. And regarding your second question, in the underground structure, so you need to define what your objective is in underground structure. In underground structures, which I feel is most of the deformations or the changes in loads occur during the early period, and particularly in the situations where rock masses or the conditions are very poor. There, most of the deformations occurs within hours also. But the people are, I think, they lag. The lag between the installation is like that. People don't consider it. The instruments to be installed at an early stage. They take some time before the instruments are put in place. So they are fear of that these instruments may get damaged or something. But for arresting or for recording the earlier deformations, if you can one of the two targets or something like that can be installed, then that will give you very good information for the project here.
Thank you, sir.
Thank you very much.
So any more questions? Otherwise, the questions are there in the chat box. Sir, we can take one by one.
Yeah.
If it is it visible to you, sir?
Yeah.
Yeah, so we can take all the questions one by one. Means first question is at 11:22. That is from 115 Patiala. Yeah. So, sir, means question is somewhat longer. So better if you can read yourself the questions.
Okay, yes, the first जो है, I think as per the Dam Safety Act rules, temperature of embankment dams needs to be monitored. For that purpose, what type of instruments are, we can use the vibrating type, wire type instruments, because those are to be embedded in the dam body, and later on those can be monitored. So that's the answer to the first part. And then the second, in a new embankment type B. Yeah. So regarding these piezometers, I have got one very good observation. So normally we install these vibrating wire piezometers during construction of the dam. So once embedded, but if you are not taking any precaution, or you are not installing it properly, and you are not extending those cables with precaution, so it has the possibility of being damaged. So the cables may get damaged, or it depends upon the accuracy of the instrument also. So in that case, I have got one suggestion. In addition to these vibrating wire piezometers, you can do one thing at one or two sections. Although I am not saying that you go for completely for mechanical type instruments or the open standby piezometer types, but at one or two sections, you install those mechanical type or the simple open standpipe piezometers also, which can give you confidence that you can compare that data with the installed instruments, vibrating wire type instruments also. It gives you some confidence, because the open standpipe piezometers, it cannot be wrong. It will not give you the wrong data. It always provides you the correct data. All that you need to do is you have to go there, you have to put in one water level indicator in your standpipes and then monitor the levels. That's what it needs. So once in 15 days or once in a month or something like that, or during the monsoon period, you can increase the frequency. But in addition to these vibrating wire type piezometers, you can have some certain sections using the mechanical type instruments also. That is answer to the first one. And coming on to the next, our dam is completed in 64 most of them. Okay, the resistance type units, so one has to contact the vendors or some other vendors if those can be rectified or not regarding the resisting type piezometers. So once one can explore the possibilities of revival of those instruments. Second part is dams are stable all these years, 60 years. Shall we stop these instruments as the embedded instruments have served their purpose? No. Second part, I'll not say that you should stop it. One should continue monitoring the data. We don't go by the years. With the passage of time, many changes and occur also, and so those have to be, the performance of the structure needs to be assessed continuously. There are many standby piezometer holes. So if those standby piezometers have been blocked, you can get them again. Washing of holes can be done, or you can take up some dry drilling in those, something you can, I think, get it, those instruments operational once again also. It is because these structures, the safety of these structures have to be ensured, so we can revive some of the instruments. More than 60 meters, the cost. Don't go by the cost. But don't go by the cost. You should fix the priorities. Priority should be your monitoring data rather than the costs. So even the Dam Safety Act also says that you have to go for monitoring and instrumentation. What's the fifth one?
Sir, sorry, sir.
Yeah, yes, please.
सर फर्स्ट क्वेश्चन में जो आपने कहा था टेम्परेचर वाइब्रेटिंग वायर थर्मामीटर्स लगाने, उसमें सर एक पॉइंट मिस हो गया. उसमें लोकेशन भी पूछा था कि एम्बैंकमेंट टैग में लोकेशन कहाँ हमें थर्मामीटर लगाने पड़े.
वो डिजाइनर्स डिफाइन कर देते हैं नॉर्मली एट डिफरेंट, जो भी वल्नरेबल समथिंग सेक्शंस रहते हैं और डिफरेंट सेक्शंस में करते हैं.
मतलब सर अबटमेंट्स में और अपस्ट्रीम डाउनस्ट्रीम में एक ऐसा कुछ कर सकते हैं.
अबटमेंट्स नहीं, वो तो बेसिकली आप पहले तो डैम बॉडी के अंदर ही आप करिए. आप फर्स्ट ऑफ ऑल तो अबटमेंट्स में तो आप एम्बिएंट टेम्परेचर्स भी कर सकते हैं, कोई दिक्कत नहीं. वो तो एम्बिएंट टेम्परेचर तो आपके पास आ ही जाता है, ठीक है ना. तो एम्बिएंट टेम्परेचर आ जाता है, आपको एम्बेड करने हैं डैम बॉडी के टेम्परेचर्स के लिए.
कोर एंड शेल में सर, है ना.
हाँ, शेल में डैम बॉडी के अंदर में, ठीक है ना.
ठीक है, थैंक यू सर.
ठीक. Okay. As you have mentioned that in the fourth, many piezometers borehole depth run it's more than 5,005 crores. Don't go by the cost here. So let us fix our priorities. Our team dam gallery fills with water up to some meters. If we stop pump out of water, if we install digital read units during the gallery fill. What is that? I could not understand point number 5 of yours.
So Mr. Arun is there. I request you to please elaborate your question.
Yeah.
Will they withstand?
गैलरी में इंस्ट्रूमेंट्स लगाए हुए थे सर, पीजोमीटर्स के एनालॉग
Yeah.
टाइप।
Those instruments
तो
are
अभी सब
embedded instruments or
नो एम्बेडेड जो भी थे वो बाहर थे सर, डैम के बाहर आ गए थे।
okay
डैम
ये
के
these were the mechanical type instruments, no?
यस सर।
Okay. No, I don't think
अभी
if you take precautions, those will harm something. Those will be damaged. But one should do pump out the water regularly. Yeah, so we should not let it stand over there still. Okay. Yeah. So
डिजिटल रेकमेंड डिजिटल लगाना ठीक नहीं है ना सर, अगर
नहीं,
गैलरी फिल हो रहा है
नहीं अभी rather in our old dams, so you can go for it, but you can search it out from the vendors whether those are available in the market and up to what pressure or something, what kind of head they can sustain water. Yeah, so that
Okay.
needs to be answered by the manufacturers. Yeah.
Okay.
ABC.
So
Yeah, so this is a very good question by ABC, something you had.
जी.
They were, what are the microseismic instruments? How the observations from these instruments are useful for health monitoring of dams? Whether these observations are needed for dams in Zone 3? So, of course, these can be installed in Zone 3 also. Coming on to the Tehri Dam, it is Zone 4 or 5, something like that, and it has been designed for that. So during the earthquake, some changes might occur to your dam. Some to witness or to see the effect of those earthquakes or seismic conditions, one should have the instruments, and from there you can get the acceleration and other things, and then related with your dam safety. What is the purpose of strain meters and strain meters? I've already told that strain meters and stress meters are used to monitor the changes in stress at various sections in the dam. What is the purpose of no stress, no strain meter? The purpose of the no stress, no strain meter is so the 5 strain meters, those measure the strains in the concrete body, okay, concrete dam. And the 6th strain meter is put in a chamber in an enclosure which we feel is under no stress conditions. But even then, some stress might occur, come on that system, which may indicate certain kind of microstrain. So all the strains from all the other 5 strain meters have to be adjusted with respect to the no stress, no strain meter. That is the basic purpose of no stress and no strain meter. How long the temperature meters are taken in a concrete dam, particularly during construction, during first filling itself, and later on those embedded temperature meters can be monitored, but the frequency can be increased, something like that. But the basic purpose of these temperature meters are during construction phase to monitor, to schedule your concreting. The frequency of taking observation. Seepage is 1 month as per guidelines for dams in operation. Yeah. So regarding this, the frequency of observation of seepage through dams, although it's 1 month, but seasonal during the different monsoon season or something like that, you can vary the frequency. The frequency can be changed during that period or some other before monsoon and after monsoon. So those frequency can be varied, but depending upon your preferences, your requirements. Water seepage. See, this purpose of this V notches in our dams is to measure the seepage through the dam body. And we install the V notches at different elevations and in different blocks. We cannot expect the whole dam to behave uniformly. The seepage in throughout the dam body cannot be uniform. Maybe certain part of the sections, maybe the end blocks which are awarded against the abutments, maybe seepage might be, you may witness more seepage through those blocks. Maybe in certain sections or certain blocks wherein you will witness higher quantity of seepage. These V notches tells us not only about the total amount of seepage, but these indicate which section is most vulnerable, and then you can concentrate on that. Suppose the end blocks, in one of the end blocks you are witnessing heavy seepage or more seepage, then you can go for some remedial measures in the abutments. You can go for grouting and other things. So based upon those measurements, you can have some remedial measures. So one should have these V notches at different elevation in different sections, and of course the finally the total seepage through the dam body has to be monitored at the sump level of the from where it is being pumped out. Yeah. Exams are paid in 6 years. Yeah, ABC एक class ले लेते हैं. Whether there are many instruments to identify the source of upward movement. Here, upward movement of water in the toe drain to trace the flow of path. Nowadays, there are many methods, techniques, non-destructive techniques are there, methods are there, which can be employed to study the flow path also. Some geophysical techniques can be adopted for certain situations to define the flow path also. So those things are available. Those can be discussed and with the appropriate agencies. Of course, CSMRS has done health monitoring of many dams, so we can help you out. But that requires discussions. Regarding this calibration of instruments, these are done in the manufacturer's place. But once embedded, I don't think there is any instrument, there is any provision by which we can calibrate those instruments. But before installation, one has to ensure that it is calibrated and properly installed. Mr. Kiran Kumar Boloju. Again, Mr. Arun has one dam is Lime Surki Masonry Dam and earthen planks and 60 years old. We do not have historical design parameters and permissible limits. How to arrive at the permissible values for many parameters that we obtain from instruments? Scale meter, joint meter. I don't know whether these instruments have been installed there or not, something. So, but this requires detailed discussions to how what kind of instruments which can be installed there, something, and once and
Have been installed,
yes,
sir.
instruments
Already
have been
these
installed there.
instruments
Okay, so depending upon the
of construction.
by the time of construction, are these instruments in working condition? Are you getting it monitored, getting the data? Many of them are working. You are getting the data. You are getting those data. Are you analyzing those data also?
Yes, sir.
Further? Yeah? You,
Sir,
so those are giving some consistency in data is there.
Few instruments, many are inconsistent.
Okay. Many are consistent. Then actually with regard to your structure, so the detailed discussions will be required. So one has to study the structure and other things also. So only then we can arrive at some design parameters or permissible limits. Na? So as of there's no thumb rule as such which can provide you the permissible values.
Some geophysical methodologies may help in assessing these parameters.
These parameters.
Yes.
Many geophysical investigations basically help us to monitor the health assessment of any structure through non-destructive. It is non-destructive.
He was talking about some design parameters also.
Design parameters, no, geophysical will not help you out. Basically, on the type of the structure or the size of the structure and other things, and the instrumented parameters, which they are monitoring, what kind of parameters, what are the values and other things. Based upon that, one can suggest.
Okay.
And so whether any distress is there, whether they are witnessing any distress or witnessing any heavy quantity of seepage or something like that, those things can be analyzed. ऐसा नहीं है, कर सकते हैं.
Okay,
We can do it, but that requires a detailed study.
Okay, sir.
Permissive. Uplift pressure meters, I think that's very simple method. When you have got the uplift pressure meter data, uplift pressures you have got along the gallery, and following the IS code, you just 6512. I think it's 6512. To follow that code, it provides you the theoretical values of uplift pressures at different sections. At the gallery, at the dam heel, at the dam toe, you plot that, you draw that uplift pressure diagram, theoretical diagram, as well as your measured pressure diagram. From there, you will see whether those are within limits. What's the limit of convergence? Oh, convergence limit. Convergence limit, it depends upon the size of the structure first. Number two, it depends upon the rock conditions. So for each and every condition, the limits of convergence are quite different. But one thing is there. So normally or maximum convergence which we can allow is 1% of the size or the span of the structure, span of the tunnel or structure, maximum. But for the sound rocks, if you that cannot be applied to the sound or the competent rocks, so that relates to your weaker kind of materials wherein we can allow that. Another factor here is the convergence. It is related to your fining lining also. The excavated profile of the tunnel is done in such a manner that you accommodate the minimum thickness of your lining also. So there also you are allowing certain amount of convergence, maximum convergence, but that depends on the type of structure, size of structure, and the ground conditions. So I think I have answered this. Time lag, timely installation of instruments, saving them for change damages issue at many projects. Yeah, this question I think has to be answered by one and all. Everyone has to put in efforts to install those instruments, and efforts have to be put in to get rid of this, I think, problem. One takes, sir, we have HAW civil in PH. Foundation of kilometer long and how to assess the stability of HRT. So does it by at-risk tunnels? So stability of HRT, if you are not witnessing any seepage through it, you are not witnessing any erosion, through the water conveyance system, then you can assume it as a stable. You are not witnessing any surface settlement, or you are not witnessing any excessive seepage rather. So you can assume it is safe. I think visual inspection ही हो सकता है. I don't think कि वो if you are witnessing some certain things, you are seeing some sort of um, chunks of concrete or chunks of rock coming into the water conveyance system. So then you can go for the health monitoring or assessment. But one thing is there. So for the headrace tunnels working under pressure, the worst condition is when we empty it, when we deplete it. That is the worst condition, because the surrounding rock mass is charged, and the conditions gets changed. The things which are in equilibrium conditions, that becomes, that gets changed, and although the external pressures are acting on there, but internal pressures you are removing. So keep that in mind. If that is utmost important, or that's an emergency situation is there, only then we deplete it. I think it's the same question. Yeah, regarding this, Arun, I think PS for PSPs. So one should go for the guidelines. One guidelines by Central Water Commission has been prepared, and these are available on their website itself. So one can get advantage of those guidelines and on instrumentation. So it's there. I think I have answered all these questions. If instruments are not working, so if you are not able to, whether you are able to repair it or not, but cables, of course, can be repaired, or those can be rectified, but nothing can be done with the instrument that has been embedded in the dam. What is the frequency of instrumentation in barrages and dams? So those frequency also, if you refer to that instrumentation manual prepared by Central Water Commission. So, but then I think that will be helpful to you. Any digital replacement for old readout units, you can contact the vendor or the manufacturer. So if something can be done. What is vandalism? Okay, yeah. So vandalism is if someone, so suppose I am responsible for the instrumentation, and you are responsible for the construction. So I'll take it in this way. So I am looking after the instrumentation, and you are looking after the construction. My instrument is retarding your progress, and then you may take a piece of stone and then damage that instrument. That is vandalism. Or vandalism by local nationals, sometimes who are on agitation because of your project or other things. They can also vandalize. I think I'll take the relevant questions. So why the minimum number of instruments have been or not been installed? Because those instruments depend upon your type of structure and your size of structure, dimensions of your structure. That's why number of instruments have not been installed. Quantity has not been mentioned in that Dam Safety Act, but it ensures that the instrumentation has to be done. So later, those have to be taken care by the design people or the developers. Permissible limit of settlement, I have already told maximum 1% permissible limit in earthen embankment dam is there. I think I have already answered. And we are unable to identify their locations now. We have instrumentation drawing. How to trace? If you have got the instrumentation drawing, I think you can locate it. Yeah. Is it impossible?
It's बाहर
हाँ.
सर कुछ आइडेंटिफिकेशन मार्क्स नहीं है सर और सभी वो वैंडलिज्म की वजह से वो सारा
Okay.
में तबाह हो
Vandalism. देखा ना, vandalism आ गया ना, I think. That's good. Vandalism आ गया. So you have defined
Right,
the
sir.
vandalism. But I don't think if something has been damaged like that can be. So at the most 1 or 2 meters you can excavate and see whether the damage is beyond that. So that's what you can do.
सर
Like
पाइप्स अवेलेबल है सर पाइप्स अवेलेबल है लेकिन
pipes available
कहाँ
है
से
but
आ रहा है
वो
पता नहीं
pipes available, those pipes might be damaged at the surface itself, na?
या सर
Around
सरफेस
the
पे
surface
डैमेज
ही
है
हुआ
सर
होगा ना. You can expect half a meter and see whether damage is beyond that or not. So then you can again revive them.
लेकिन वो कौन कौन सी जगह
वो तो वर्टिकली ही होगा ना. पाइप तो वर्टिकली होगा ना. पीजोमीटर इंस्टॉल किया है, वो ऊपर स्टैंड पाइप पीजोमीटर है तो वर्टिकल ही होगा. तो
सर ये है ना सर और प्रेशर सेल
और प्रेशर सेल के किसके हैं?
और प्रेशर सेल्स के लिए
आपने
है सर
पीजोमीटर का है ना. तो आई थिंक स्टैंड पाइप पीजोमीटर है ये.
नहीं मीटर नहीं सर और प्रेशर
ओके
सेल
ओके
और एम्बैंकमेंट से बहुत सारे लोकेशन से आए हुए
नहीं
हैं
वो
सर
ओके अनटिल अनलेस दैट्स व्हाई मैंने बोला था कि ना जो टैग नंबर्स है ना उसी से आप आइडेंटिफाई करते हैं. तो टैग नंबर्स हैव टू बी provided. Once you will not be able to know the location of the instrument. That's very difficult. That's tag numbers nahi hai, then that is very difficult to identify the locations of the instruments. Then one cannot then. One cannot. There's no thumb rule. Yeah. So it's good that the CWC guidelines are available, manual is available. So online, so one can download it and use it. Yeah. Sir, you have shown Kaleshwaram Raj failure. So yeah. If so, how was it rehabilitated? So that I cannot say beyond whatsoever I have said. Kaleshwaram Raj, it is under investigation, and those remedy measures will be suggested and I think undertaken in near future. Yeah.
Okay.
Any guidelines underlines IS codes are there for reference. Yeah. So you can one can refer those to those codes. USBR guidelines are there. So one can refer to those USBR guidelines also. So, okay, I think I have covered all the questions which have been put up to me. Yeah.
Yes, sir. Thank you very much. Thank you very much. The questions were not so easy, so complex because it's somewhat related to some design parts also and related to your analysis parts, investigation parts. So completely the means all questions covered the topics. And topic itself is not so easy because dam instrumentation we are doing and we are not successful enough to take it further. Sir, thank you very much having for your awesome presentation. Definitely, it was very helpful to all of us. Earlier, also I attended your lecture and I have read your paper, so I am always benefited from your delivery. And thank you all the participants also for raising these questions. by raising questions, others are also getting benefited, and means you have covered all the queries means in this topic. All means we thank you all for patiently learning, listening to Sri Haridev Sahab, and his experience has spoken that many things are out of the book. So he has shared his experience further. At many places, he has suggested that you have to means if you need further knowledge or further your problem is there in the dam, then you can contact CSMRS also. In details, many things there they have to do in details. So you first of all you have to approach them, and then they will suggest your some remedial measures. And certainly somebody has asked your contact number. Sir, with your permission,
Yes, you can provide. Yeah, you can provide my email ID. Yeah, no problems. Anybody
yes,
can
provide them too.
Yeah.
So thanks a lot. And as usual, we are providing all the recorded videos and presentations to all the participants here before the start of the next session. Means in 2-3 days, I will provide it. And up to now, we have given all the recorded videos of the presentation along with the PPT or in the PDF form itself to all the participants through email. So I hope that all will be getting it. If someone is not getting it, they may ask me. I'll further forward it to you. So thanks a lot, sir. Thank you all very much. And we'll be in the next session. Will be on 14th of January, which is Sankranti. Although but we are open. So I hope that on Sankranti also you'll be enjoying our sessions, and that session will be the reservoir sedimentation, one of the important topic of this dam safety assessment. With
Okay,
this,
thank you.
with this, I conclude the session, and I really thank you, sir. Thank you.
I thank the National Water Academy for taking up this instrumentation subject to this scale, because this is a neglected subject up till now. So we all have to work towards the instrumentation in dams. So thanks a lot for NWA, particularly Dasam, and thanks the participants for making it a very memorable presentation, memorable session for me also, because of your interactions, the kind of interactions which you have shown. So it was quite good for me also. These interactions help the speakers also in improving the talks in future also. Thanks a lot. Thanks everyone. Thank you, Dasa. So
thank you, sir. We'll please meet you. We'll see you. Thank you very much.
Thanks a lot. Thanks a lot. Thanks.
Have a nice day. Thank you.
Thank you.
The contact details share.
Yeah. I'll in chat box itself, I am sharing the contact details in the chat box itself. Okay, उधर का हो गया। हाँ, इसमें लिखे था 979717311033 Dr. Haridev CSMRS. 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 बस इसको सेट कर दीजिए। CSMRS चला गया था। CSMRS हाँ चला जा रहा है। हाँ चला जा रहा है। हाँ हो गया। ठीक है ना, इसको कॉन्टेक्ट So we have shared the contact details. Further, we'll share in the the email address. Right now, I don't have. I will get it and I'll share it. But contact number I have shared it. Thank you very much.
Thanks.